Calculus BC, lesson 7.4, exponential growth and decay. So we start getting back to applications, but we have this little sneaky thing where we say, oh, by the way, here's another way to do integration. This is called separating variables. If you have f of y and g of x as part of a differential equation, you can break them apart and then integrate each side. It's actually not too bad. So we look at this equation as dy dx equals x squared y squared, and we separate the variables, so we get dy over y squared equals x squared dx. Then we integrate, that's y to the negative 2, add 1, and divide by that, we get negative y to the negative 1 equals x to the third over 3 plus c. Now this is when we will actually find the c value. And people say, well, can't I just do it at the end after I kind of sort y here? No, this is the best time to do it. I've tried it both ways. It's kind of a hassle. Negative 1 equals 1/3 plus c. C equals negative 4/3. So we've got a negative y to the negative first equals x to the third over 3 minus 4/3. Divide out that negative, common denominator, y to the negative first equals negative x to the third plus 4 all over 3. This is y, 1 over y, so we flip it, and we just flip the other side too. We'll get 3 over 4 minus x to the third. Notice that there's going to be a hole because we have a rational function with a variable on the bottom, and that hole would be at this spot here. S is the third root of 4, which is a little bit bigger than 1. We'll say that because if we look at this, we say this differential equation only works on the continuous part of the function. So the function has got a discontinuity at third root of 4, 1 point something or other, and it'll be continuous then. The domain, that is, will go from negative infinity all the way up to, but not including, the third root of 4. After the third root of 4, we might have a different differential equation. We can't say what's going on over there. But certainly that is nothing to worry about. That's not a typical part of any problem. So that's something you'll practice doing those kind of problems. Back to applications, here's exponential growth. So, hey, shockingly, we actually use that. If we have something that is growing or decaying, the more material it is, the faster it grows or decays. So we use a variable k as a growth or decay constant, and do our little trick we just did. Keep it, and we'll bring it up here. And this is the form you've seen it in, hopefully, in a pre-calc class. We say that plus or minus e to the c is some a value, and we just write it as y equals a e to the kt. A is the initial amount typically, and it's typically written as y naught. So that's how it goes. If k is greater than 0, we've got growth, money, populations. K is less than 0. We've got decay. Lots of things, typically chemical breakdown, nuclear breakdown, things like that. So there it is. I like writing things down, but I also like keeping you on your toe. So this is how continuously compounded interest works, and that's rare. Usually banks compound monthly. But if you think about it, a bank, you put $1,000 in on January 1st, and if they don't compound, which just means calculate the interest, and you take it out on December 27th, and they say, well, we're paying you 10% yearly, but we haven't actually calculated yet, so here's your $1,000 back. So they actually usually compound monthly. But they can do it anything. They can do quarterly, monthly, daily. It's just when they actually hit the calculate button on the computers. We'll go with that from there. So I'll show you how to do both. So regular interest looks like this. The amount is your initial amount times 1 plus your interest rate. Our textbook uses the letter K, but I use the letter N for compounding to the NT. N is compounding. So if you're compounding 12 times a year, it's 12. R is your rate. T is, the years. And then compounding continuously is just the original amount e to the RT. So notice we don't have to worry about how often we compound it. It's continuously. And I am not doing the math here, but if you did quarterly, and you should blast this out on your calculator, but it's not that hard, you would get $1,319 and 7 cents. If you did it continuously, you would get $1,324 and 26 cents, to which most people say, well, big deal, it's $5 and change, and that's over 8 years. Who cares? Well, if you're a multi-million-dollar investor, you would care. Actually, it adds up. Other things that compound continuously are population when the numbers are big enough, because there's so many people that it's more or less like they're continuously, or so many animals or so many amoeba continuously getting bigger and bigger, and that's growth. And like I said earlier, you have nuclear or chemical breakdowns where there's just so many atoms that the breakdown is happening on a continuous basis, and that's decay. So these are typical problems you'll see out there. I did a lot of nuclear ones in college, becoming a mechanical engineer. I think I had a minor in nuclear engineering. So what's the half-life of a substance? Well, here's the interesting thing. You say half-life, so you want to have half y naught when you start with y naught. If I had 100, I want 50. If I had 10,000, I want 5,000. It's just right there. And we throw this negative up there. It's artificial, but don't worry about it. So these cancel. You get 1/2 equals e to the negative kt. You take the natural log of both sides. And you get negative kt, I'm going to write it over here just for the fun of it, equals natural log of 1/2, and divide through by negative k, gives us our half-life. And by the way, k is usually a negative variable, so it kind of cancels out. We get negative 1 over k times the natural log of 1/2. I don't memorize this at all. I simply play with it. That's what I do. And if you want to memorize it, it works fairly well. You're just looking at natural log of 2 over k, assuming k is greater than 0. And again, if it's not, you just do the math and see where it takes you. Sometimes you want to use a different base. The base we've used so far, of course, is E, which I think is nicknamed after Euler. I'm not really sure. I should look that up. So you got a population growing. It's hornets, because we all have a population of hornets growing outside of our house, and they are starting at 10 on May 1st and growing to 50 in 30 days. So we can just write out an equation and use whatever base we want. It grows by a factor of 5 in 30 days. So we could write this as 100. I want to know how long it takes to do that. No, actually, let me write it out differently. Y equals our original amount, 10, times 5 took 30 days, t. So if I put 30 in for t, they cancel. I get 5 to the first, 5 times 10 is 50. So there's a model. Hey, I just made it up. It's got a base 5 and it works. Want to know how long it takes to get to 100? Again, take the natural log of both sides. Actually, my bad. Divide both sides by 10 first. Then take the natural log of both sides. No, don't take the natural log of both sides. Not doing my job very well here. Yes, take the natural log of both sides. Goodness gracious. T over 30 times natural log of 5. Divide by natural log of 5. Multiply by 30. Divide by natural log of 5. Multiply by 30. And we get t equals 42.920 days. You could model this exponentially, although the numbers are kind of small, so it'd be kind of weird. You can model it lots of different ways, but this one works pretty well. Carbon-14 dating, classic example. I looked this one up, and the guy won a Nobel Prize, came up with this. It's pretty cool. The ratio of carbon-14 to carbon-12 in your body is always constant because you're always breathing in carbon-14, which comes from solar radiation impacting carbon atoms out in the air. So they can take a sample and see what the ratio is, because once you die, you stop ingesting new stuff, and the ratio starts changing. This is kind of cool stuff. So we're looking at a half-life of 5,700 years. So we got to do a little math first. Model this as A equals the original amount times half times t over 5,700. And we want to know what percentage is left after, we want to know how old the sample is with 10% left. So let's do some math. Thinking for a moment here. Why would we use 90%? I don't understand that. Oh, 10% is decayed. And so we want to do 90% left. Read the question wrong when I typed it up. My bad. So 90% is left. So we got 0.9 equals a naught 1/2 t to the 5700. Cancel. Natural log both sides. Divide, multiply. We get t equals about 866 years. So that's how they do carbon dating, and it's not quite that accurate, but it's accurate enough to give some good data. And I believe this is last but not least, Newton's law of cooling. He noticed that things lose temperature faster when they're hotter, and the ambient air around them is cooler. And then as it gets closer and closer to the ambient temperature, it slows down. So if you were to look at, here's your ambient temperature, and you take something that's hot like that, it loses it in exponential decay. This is your surrounding temperature. I've actually seen it called lots of different things. This is your initial temperature. K is your constant, which you don't know. You gotta go figure it out. So here it goes. Hard-boiled egg at 98 degrees Celsius is placed on running 18 degrees Celsius water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees Celsius? So there's a lot going on here. We start with T minus 18, the surrounding, equals the original 98 minus 18, the surrounding, e to the negative k t. So we've got a nice little setup here. T equals, do the math, add 18. No, subtract those two. 18 plus 80 e to the negative kt. We know that t equals 38 when little t equals 5. So we plug that in, and we get I'll let you do the math. K will equal 1/5 ln of 4. You can put that in as a decimal if you want. So that tells you the formula you're looking for. How much longer will it take? Well, you got to solve that. You take t equals, 20 equals 18 plus 80 e to the negative 1/5 ln of 4 t. Blast out all the math and say t equals 13.3 minutes. It's just another application of decay. Here's another problem that you can put in your calculator and do an exponential modeling of. I am not going to do it here just because I'm out of time. But it's something you definitely try. If you do it right, you should get something like t equals 4.5 plus 61.66 times 0.9277. Notice we went decimal on this one to the t. And then you can use that model to do whatever you want. You can plot it, look at the scatter plot, and see how your plot looks relative to that. So give it a shot. A lot there. That's it for today. Happy mathing.